Hello. In this video, I'm going to just work through the Chapter 2 notes, and you can follow along, you can skip ahead in the video, feel free to pause it, whatever you need to do. In the first section, we're going to talk about just describing graphs. We're going to introduce some vocab and work with interval notation a little bit here. We're also going to take a look at piecewise functions. So we say that if the graph of a function rises when moving from left to right, that is called increasing. If it drops from left to right, so like here, it's dropping, we call that decreasing. And if function values stay the same, we call that constant. So here, intervals where it's increasing, well, that's happening right here. And so that is, again, thinking about my x values, interval notation, from 3 to 5. It's decreasing then, negative infinity up to negative 1. And that's a union symbol. It's also decreasing from 5 to positive infinity. And it's constant then from negative 1 to 3. Relative maximum and minimum. These are the highest points in a given location on a graph or the lowest points. Let's take a look here. Here you can see we have two relative max. Oops. And sometimes we just call these max and mins. Okay, so you could, a lot of times we drop the relative and we just call it max. Alright, let's take a look at piecewise functions. This is a piecewise function. It has several pieces, so we call it a piecewise function. And really what it's saying is use the function x. It depends on what my x value. If x is less than or equal to 0, we need to use this piece of the function. If x is between 0 and 2, then we use this piece. And if x is greater than 2, we use this piece. So let's just try this out. F of negative 3. Well, you could see x is negative 3, so we need to use this piece of the function. Well, in that case, my y value is just negative 3. How about for f of 1? You can see x equals 1. That means we're going to need this piece of the function, all the values between 0 and 2. So I have negative 3 plus 1 squared. That's going to give me negative 2. You can see the last one here, f of 5. X's value here is greater than 5, or greater than 2. So I use this piece. So I have to put 5 in place of x. That gives me 1.5. Now, to graph the function, there's several ways of doing this. I'm going to show you the table way. Focus here on these numbers. So we're going to want to pick some table values less than 0. So I'll put negative 2, negative 1, 0. I'm actually going to put 0 in twice. I'll explain why in a second. 1, 2. I'm going to put 2 in twice. And then I'll put a couple more, 2, 3. I guess I have it in there several times. Alright, so let's go ahead and get started. For these values, I'm going to use the first piece, because these values are all less than or equal to 0. So in each case, the y value ends up being negative 3. Now, I put 0 in there twice. I'll get to this in just a second, but we want to actually plug that in. Even though this is part of the first piece, we're going to need that value. So I kind of scribbled it out because it's not actually on the graph. But if 0 was in this range, if this was an equal to symbol, it's not, we would plug 0 in. So negative 3 plus 0 squared is negative 3. I can then plug in 1 and 2 to the second piece. Oh, sorry, this is getting kind of messy. So plug in to the second piece here. So 1 squared is 1 plus negative 3 is negative 2. Plug in 2. 2 squared is 4 plus negative 3 is 1. And then this is the third piece. Excuse me. Again, since its x is greater than 2, this isn't really part of my equation, but it's going to be helpful when I graph to know where that would have ended up. And so when I plug 2 in there, 2 divided by 2 is 1 minus 1, this would be 0. When I plug 3 in, 3 divided by 2 is 1.5, minus 1 is 1/2. And when I plug 4 in, 4 divided by 2 is 2 minus 1, which is 1. I now plot these piece by piece. So the first piece has points at negative 2, negative 3. I'm using these. Negative 1, negative 3, and 0, negative 3. And we can see the pattern that this would keep going this direction. So that's the first piece. At x equals 0, it shifts. I'm going to go ahead and plot these 2 points next. You know what? I think this would be helpful. Okay, so now I'm going to plot 1, negative 2, and 2, 1. Here's the deal. We don't always connect it to here, but since this number is negative 3, we are going to this time. Let's look at the next one. This is the third piece. I guess I never wrote that in there. And so this third piece is actually 2, 0. It's down here. Do you see that? I made that an open circle. There's not actually a point there, but it would be there if we were graphing this as an equal to, but it's not, so we just leave it as open. 3, 1/2, and 4, 1. And so we see this graph has a skip here, or a hole we would call it. So here it's all continuous. It connects up. The orange open circle and the purple closed circle match up. But then here, the orange closed circle is here, the open blue circle is here. So we do not always connect those dots. So that's how we graph piecewise functions. Let's take a look at example 7. There are some shortcuts. Feel free to use them if it's helpful. But actually, I'm going to use purple on this, orange on this, and blue on this. So purple, xy, we want numbers less than or equal to 0. So we're going to go negative 3, negative 2, negative 1, 0. When I square those numbers, I get 9, 4, 1, 0. For the orange second piece, I've got numbers between 0 and 2. I'm just going to do 0, 1, and 2. And I am going to scribble out 0 because that needs to be an open circle. You see that? Alright, here we go. So when I plug 0 into this equation, there's no x to plug it in, so my y value is just 4. All along here, these are going to be 4. When x is 1, y is 4. when x is 2, y is 4. Alright, let's look at the third piece now, x, y. I want values that are greater than 2. I'm going to still plug 2 in, because I want to see where that open circle would be. And so I plug 2 in, 2 minus 1 is 1, 3 minus 1 is 2, 4 minus 1 is 3, 5 minus 1 is 4. And now we can go ahead and graph these. Let's start with the first piece, the purple. Negative 3, 9's off the chart, negative 2, 4, negative 1, 1, and 0, 0. So I've got a parabola here, at least half of one. Now for the orange points, I'm going to have an open circle at 0, 4. I want that to be open, open, like really open. There we go. No confusion now. 1, 4, and 2, 4. And these are closed. And then the blue. 2, 1, that's going to be our open circle. 3, 2, 4, 3, and 5, 4. And so this piecewise function, you could see, has 3 pieces. And it matches, right? X squared, that's going to be a parabola. Y equals 4, going to be a line. Y equals 4. And x minus 1. If I wanted to, I could graph this with a y-intercept of negative 1 and a slope up 1 over 1. Do you see that? Alright, so those are piecewise functions. Let's take a look at this example here. X minus 2 when x is not equal to negative 2, and x equals 3 when x is equal to negative 2. So let's go ahead and make a couple tables here. And again, if you see some shortcuts, please use them. Okay, so we want all the values when x is not equal to negative 2. So I'm just going to go negative 4, negative 3, negative 2, negative 1, 0, 1, just to get a feel for it. And you might be saying, wait, Rassi, why are you doing this? Like, it's not supposed to be equal to negative 2. But remember, we want an open circle at that spot, and we need to know where to put that open circle. Now, the purple, this is kind of interesting. There's only one point. It's only at negative 2. I'm not going to worry about anything else. I'm just going to put negative 2 in. Alright, so when x is negative 2, let's do this purple side first. Y value is just 3. So there's a point at negative 2, 3. Now let's take a look at the blue ones. Plug negative 4 in. Negative 4 minus 2 is negative 6. Plug negative 3 in. I get negative 5. If I plug negative 2 in, I would get negative 4, but remember that's an open circle. Negative 1 then is negative 3. 0, negative 2, 1 is negative 1. So we can see a pattern there. When x is negative 4, it's off the chart. When x is negative 3, we're at negative 5. When x is at negative 2, we've got an open circle at negative 4. At negative 1, an open circle at negative 3. 0, negative 2, 1, negative 1, and so on. Okay, so you can see this function has a piece here. At negative 2, there's just one value up here, and then the rest of these. And so if I asked you to look at the graph, and I said, hey, find, let me do a different color, find f of negative 2, on the graph, you would go to x equals negative 2, you would go up to the function, and you would go over and you'd say, oh, it's equal to 3, which is what we see over here as well. All right, now it's asking us for the domain and range. Do you remember what domain and range is? Hopefully you're thinking x value and y values. Domain here, x values, it's going to be all real numbers. The way I'm doing this is I'm looking and I'm saying, hey, any x value I pick, there's always a y value. There's always a spot on this graph. There's No matter where I pick, there's a spot. What about 2? You might say, well, it's open, but down here it's closed. So here, the domain is all real numbers. Okay. How about y values? What y values do I have in my graph? Well, if you look here, there's no function point here at, is that 6 or 5? There's no y values in this range. You see that? There's actually y values here at 4, at 2, and negative 5. So my range is y equal, I'm going to start at the bottom, negative 5, negative 2, positive 4. Let's take a look at 76 here. Oh, they want an equation for the function. That's the fun part. Here we go. F of x equals, and you see we're going to have 3 pieces. 1, 2, 3. The first piece there is a horizontal line at y equals negative 2. So we just put negative 2, and you see how up here is a setup for what x values? It's negative 2 for x less than 2. The second piece is at 2. My function's negative 5 for x equals 2. And then the last part is when x is greater than 2. This is the equation y equals 4. So my function is equal to 4 for all x values greater than 2. And so there's my function. All right, let's take a look at this one, domain and range for example 10. Domain here would be the x values. Here I don't have any x values out here, so I don't want to include those. So it's just when x is greater than or equal to negative 4. You see it's a closed circle. That's why I made it equal to. At 2, I want to check that, but you see there is a point at x equals 2. So everywhere we go, that's my domain. How about my y values? What's my range? Well, I don't have any y values up here. I don't have any y values down here. Okay, but everything in between here, between 4 and negative 2, there are y values. So my range is, we could write this in 2 ways. Y is greater than or equal to negative 2, and y is less than or equal to 4. Or you could make this a combined inequality, where y is greater than negative 2 and y is less than or equal to 4. We say it the same way, we just read this half backwards. Y is greater than or equal to negative 2. All right, let's take a look. Erase some of this garbage. Here we go. Equations. I know this is your favorite part, right? All right, let's think about the equation. When we have a nice little graph like this, and we could see the y-intercept, see if I just extend this line, I could see this would be y equals mx plus b. What's my slope? Let's see. It looks like it's touching here, down to right 1. So my slope is negative 2 over 1. My y-intercept, negative 4. So I know this equation is y equals negative 2x minus 4. Let me erase this extra stuff here. So if I'm going to write my function, f of x equals negative 2x minus 4. For which x values? For x's between negative 4 and 2. So I'm going to put negative 4 is less than or equal. X is less than 2. All right, let's take a look at this next equation. This equation, we see a y-intercept of negative 1. We also see a slope here, right? Up 1 over 1. So m equals 1, b equals negative 1. So my equation here is y equals x minus 1. Or you could say 1x minus 1. Fantastic. We got the hard ones out of the way. This is going to be x minus 1 for which x values? Do you see it's the x values from here to here? But we want this one to be open. So we go from 2 is less than or equal to x, or x is greater than or equal to 2, up to the point where x is, oh, I made a mistake, less than 2. You probably caught it already, right? I was looking at this 2 and should have been looking at the x value here, which is -1. So this needs to be -1, and this needs to be -1. Alright, let's take a look then at this last part. This part is a horizontal line at 2, so it's just the equation y equals 2. So this third piece is y equals 2, and that's for which x values? For any x value greater than or equal to 2. And so this piecewise function has 3 pieces. A piecewise function could have 3, it could have 6, it could have 10. Doesn't matter. Alright, that is section 1. We're going to go a little out of order here. We're going to skip to section 4. Section 4 is describing graphs a little bit further. We're going to introduce 3 vocab terms: symmetric with respect to the x-axis, symmetric with respect to the y, symmetric with respect to the origin. Okay, symmetry, hopefully you're thinking about the word mirror. That's pretty good for x and y axis. Origin, we're going to talk about this a bit more, but it's a rotation of 180 degrees around the origin. So this first one here, if you think of this as a mirror, if we look, is there a symmetry with across the x? Or that's the y, I'm sorry. No, there's not. There's not the same thing as there is on each side here. So it's not with respect to the y-axis. How about with the x-axis? We get the same thing. There's not a mirror image on this side. It's sort of similar, but it's not a mirror image. This one is actually with respect to the origin. Do you see if I spun this around? I don't know if I can actually do this or not. I don't think I can. Yeah, look. Cool. I'm so excited. It's off just a little bit, but you can see it's 180 degrees. Excellent. So that's the origin. How about this one? Does it have symmetry with respect to the x-axis? Kind of looks like it, doesn't it? This side matches this side. So this has symmetry with respect to the x-axis. How about the y-axis? Not quite. You see, if I folded this over, I would have to have kind of the same shape on this side. So they would match up. And then how about with respect to the origin? If I took this and I rotated it, I'm going to do this just because I can. I think if I center it here, not quite, right? Even if I line it up. So, only with respect to x. It could be some of each. This one, with respect to y. This one, neither. If you would fold it over, it doesn't quite match. It would need to look something like that, so it's not with y. And same way with x. If you folded it over, it would have to match something like that, and it doesn't. Symmetry, rotation, not quite. Here's why. I'm not going to curve this all out, but you can imagine if I rotated it, it doesn't quite land. You see it's on the other side of the axis. Okay, so this is none of the above. This one does have symmetry with respect to, that means that's an abbreviation you can use, the origin. All right. The next thing we're going to talk about is odd functions and even functions. If you take a second and you graph these on a calculator, you'll see that these are all parabola shaped. They get a little skinnier as you go along. And you'll see that these all look something like this, and again, they get skinnier as you go along. Okay? These are all called even functions. These are all called odd functions. These functions, even and odd, do show up besides just these exponents. It's more the idea that an even function has symmetry with respect to the y-axis, and an odd function has symmetry with respect to the origin. So which functions are odd, even, and neither? If I go back and look, this is going to be an odd function. This is going to be an even function, even though it's technically not a function, even relation. And this is odd function. The rest are all neither. So neither. All right. There's another way you can define this algebraically. We're not going to cover this year. If it talks about prove algebraically or something, you can skip that one. Just skip and leave a note. I'm just going to say if you have an even function, f of negative x is the same as f of positive x. You can imagine that f of 2 is the same as f of negative 2. They have the same y values. The odd function, on the other hand, is the opposite. So if I have a negative value, say negative 2 is negative 8, then positive 2 will be positive 8. Alright. Now it says to graph the equation and determine visually whether it is symmetric with respect to x, y, and the origin, then verify your assertion algebraically. This is the part you do not have to do this year, fall of 2020. If we graph this, I should just confirm. I know what it looks like. I don't need my calculator. It's going to look something like this. And so this is an odd function. Do you see that? It has symmetry with respect to the origin. Alright, example 6. Even, odd, or neither. Again, you can graph these, or that might be your safest bet, is just to graph these. And then look at the graph. Remember, even has symmetry with respect to what? The y-axis. Odd respect to the origin. Now, there is a shortcut here. Remember I showed you earlier? Even exponent x values are even functions. Odd are odd. But if you combine two even functions, it's going to be even. This doesn't have an x value. but you could add 1 by saying x to the 0 power. So in this case, these are all even exponents. This would be an even function. Go ahead and graph it. See if I'm right. This one, I think we can do this. We can just say this is odd. Again, graph it, take a look, see if it's symmetric with respect to the origin. This one might look odd to you if you look here. Might look even to you if you look here. But remember, it's the exponents on the x values. This is odd, this is even. So this one is neither odd nor even. Here we have that symmetry with respect to the y-axis. So this is an even function. That should wrap up even and odd. All right. Then we're going to go to section 2.5. We're going to look at functions in general. And you can see that there are, actually I was going to say 12. I think there are 12 basic functions. In this chapter, we're just going to hit 7 of them. So here we go. Here's the idea. We are going to, I don't know about you, up here when I was doing all these tables to graph, this got really tedious, and I don't like to use tables. I like shortcuts. And so what we're going to do in this section is we're going to use tables to get an idea of some basic functions. Y equals x, y equals the absolute value of x, y equals x squared, y equals x cubed, y equals the square root of x, the cubed root of x, and 1 over x. Okay? And then anytime we see something that has an absolute value, we're going to be able to use this function to help us know what it looks like. Or anytime we see a square root function, we're going to be able to use this function to help us know what it looks like. So that's really the goal here. So I would encourage you to actually pause the video and go through and fill the tables out on your own. I think it would be really helpful for you. Notice we can't take a square root of a negative number here. We can take the cubed root of a negative number, though. Kind of cool, huh? I don't know what the cubed root of 2 is off the top of my head. I'll leave that for you to punch in your calculator. Negative 8, negative 2, negative 1, 1, 0, 0, over 1, up 1, and over 8, up 2. This is a cool function, I think. I don't know why I like it. A reciprocal function. Here's why. If you take 1 divided by negative 1/2, you could type it in your calculator and see, or you can multiply by the reciprocal, and you get negative 2. At 0, it's undefined. 1. All right, so you could take a look at these. I'll maybe put it on the screen so you can pause it and compare it. But these are the 7 functions we're going to work with. All right, how are these useful? I think normally I would have you do a little activity with this. Little notation. These are all functions. And this is saying if I have a function and I add or subtract a number behind it. So let's just do a couple examples. Let's say I used the function any of the 7 that we just did. So let's just pretend for a moment that b equals 2. So I'm going to run out of space here. Let's say b equals 2. Let's do this with the squaring function. Or we could do it with the absolute value function. Or we could do it with the cubed root function. Doesn't matter. Any of those. What's going to happen to my xy values? All right. I don't think this is going to do what I want it to do, but I'll try. Yeah, I was afraid it would just get the numbers. Okay. Think about y equals x squared. If I have negative 2, negative 1, 0, 1, 2. If these are my x values and my y values, negative 2 squared is 4, 1, 0, 1, 4. Okay, and so you can picture that. 0, 0, 1, over 1, up 1, and then over 2, up 4. We get a parabola shaped. But now, what if I think about y equals x squared plus 2? What's going to happen? I think you can see this, can't you? Negative 2, negative 1, 0, 1, 2. Plug negative 2 in, I would get 4, but then I need to add 2 to it. So this becomes a 6. Same way here, negative 1 squared is 1 plus 2 gives me 3. 0 squared plus 2 is 2, 3, 6. And so notice what happens. I probably should have a nice graph here, I'm sorry. Instead of going 0, 0, I'm at 0, 2. You see it moved up 2? Instead of being at 1, negative 1, 1, and 1, 1, I'm at 1, 3. And instead of going over 2 and up 4, I'm still going over 2 and up 4. It just happens to be from a different origin. Okay? So I know that's a lot there, but plus b is just going to move the function up 2. Minus b is going to move the function down, I guess b. It depends what that number is. B. So let's try another example here. Yeah, let me just delete all this scratch. Let's try y equals the absolute value of x plus 2. So normally, notice it would just be 3, 2, 1, 0, 1. But the plus 2 is just going to move everything up 2. So this is going to be 5, this is going to be 4, this is going to be 3, 2, 3, and so on. So instead of having my graph look like this, can you picture it? It's just going to be shifted up 2. All right. Something weird. Okay, let me pause there. Quick summary, because I don't want you to lose it. This is the key idea. When it's adding b and it's outside the function, it moves up b units. When it's minus b, then it's moving down b units. Now what does this mean? X plus or minus d. How does that compare to this one over here? Actually, I'm going to leave that yellow. The contrast here, plus b is on the outside, the plus d is on the inside. So what does that look like for a function? If I look at an example. Well, before I said y equals x squared plus 2, and you see the plus 2 is on the outside of the function, it's not in the x value. Here I'm replacing the x value with x plus or minus d. So what I need to do here, instead of putting the 2 on the outside, I need to put the plus 2 with the x. Now what's this going to do? This is a little tricky. Let's think about 0. I'm just going to do positive numbers for a second. 0 plus, or for this one. 0 squared is 0, 1 squared is 1, 2 squared is 4. What about this one, though? If I want to get the origin, kind of that center point, 0, 0, what number do I have to put into my function for x? You see I have to put negative 2 in, plus 2 is 0, 0 squared then is 0. And then negative 1, plug that in, I get 1, which is 1 squared, which is 1. Plug in 0, now I get 0 plus 2, which is 2, squared is 4. If I plug negative 1 in, I'm going to get positive 1. So I don't know if this makes sense to you, but over here, this, 0, 0, over 1 up 1, over 2 up 4. For this one, I go left 2 up 0. I meant to put negative 3 here, guys. I'm sorry. Negative 3, 1, negative 1, 1, 0, 4. What do you think negative 4 is going to be? You could plug it in, right? It's going to be 4. So what happens when I add 2 on the inside here? Do you see it actually shifted these points left 2? And we ended up with this. And so when you look at an equation, let's do this equation, the reciprocal one. Y equals 1 over x plus 3. You hopefully are seeing, hey, I see the reciprocal function in disguise, right? What's happening to this reciprocal function? It's moving right 3. Since it's moving right 3, I've said right 3. It's plus 3. But what does the plus 3 do? It's going to have the same impact that the plus 2 had here. It's going to move it left 2. So this is going to move left 3. So I know without graphing any points that this is going to look like this graph, only everything's moved left 3. So instead of having my graph centered on the y-axis, my graph is going to be centered on the line at x equals 3. Go ahead and type this in your calculator. See, you get that function. Isn't that cool? Alright, so the key takeaway here is plus d inside the function. What's it going to do? It's going to move left d units. What do you think it's going to do if it's minus d inside the function? It's going to move right d. That's going to look like donuts. d units. Alright, so key idea. Add or subtract outside, move up or down, matching the sign. If it's on the inside, it's going to be opposite of what you might expect. If you're adding, it's going to go left. If you're subtracting, it's going to go right. Alright, so let's take a look here. What happens if I multiply by a number where the a is? So let's think about y equals 3. Actually, let me make this. Let me make this 4 square root of x. If you think about our xy, our normal square root of x, oops, wrong button. Our normal square root of x, we can't graph any negative numbers. We would get 0, 1, 2, 3 when we take the square roots. But here, when I multiply it by 4, what's going to happen? I'm still going to have 0. 0 times 4 doesn't change anything, but here it's going to be times 4, times 4, times 4. Do you see my graph went from this to now it's going to be 4 times stretched out. 0, 0 is still the same, but instead of 1, 1, it's going to be 1, 4. Instead of being 4, 2, it's going to be 4, 8. And so it's going to look similar, it's just going to be a lot taller. And so here, when a is a number greater than 1, we're going to have a vertical stretch to our graph. So it'll be these basic functions only stretched out, up and down this way maybe, or up and down this way maybe. But if a is between 0, 1, it's going to be a vertical shrink. And hopefully that makes sense to you, that this multiplying by a is just going to take the y values and multiply them, and so it's going to stretch them out. This one is going to be a little tricky to understand. When the c is on the inside, y equals the square root of 4x. We have our xy table here for y equals the square root of x. What happens when I put the 4 in there? Zero is fine, right? I plug 0 in, it's going to give me 0. But if I want to get 1 as my y value, I need to put 1/4 in. I don't know if that makes sense. If I put 1/4 in for x, 4 times 1/4 is 1. The square root of 1 is 1. To get 4, I'm going to have to put the number. To get the same y value as 4 in the x value here, I'm going to have to put the number 1 in for x, because 1 times 4 is 4. The square root of 4 then is 2. And then this is going to be the same way. It's going to be 9/4. When I put 9/4 in, times 4 is 9. The square root of that is 3. And so when I go to graph this function, 0, 0 is fine. Where before I had 1, 1, I had maybe 4, 2, 5, 6, 7, 8, 9, 3. Now, now I've got 0, 0, still the same. I go to a 4th and 1. I go to 1 and 2. And I go to 9/4, which is 2 1/4 and 3. Y equals the square root of 4x. So I don't know what you're thinking. It almost looks similar to what happened over here, doesn't it? It's a little different process, though. This one is being squeezed horizontally. Did you see the movement was horizontal? Where this one, the movement was vertical. Okay? And so we are going to call this a horizontal shrink because it's going in that direction. So if C is greater than 1, we have a horizontal shrink. And you can explore this on your own. But if C is bigger than 0 and it's less than 1, we're going to have a horizontal stretch. All right. I know there's a lot going here. We'll finish this up here in a second. What's one that I haven't done yet? Let's do y equals x cubed. No, I don't like that idea. Let's do y equals square root of x. I know we just used it, but it'll be okay. So I'd like you to think about that. What about negative signs? What if I put a negative in front of the function? You see here? What's that going to do? Well, let's try it out. Do purple. Y equals the negative square root of x. I've got xy. I could still put 0, 1, 2, or 0, 1, 4, 9 in. Notice I'm skipping because I don't want to deal with decimals. So I picked these numbers. They're nicer. The negative square root of 0 is still just 0, but the negative square root of 1 is negative 1. The negative's on the outside, so that's okay. Square root of 4 is 2 with a negative sign in front of it is going to be negative 2, negative 3. And so if we look at our graph, zero, 0, 1, 1, 4, 2, and 9, 3. look something like this. Purple one though now with the negative sign in front, 0, 0, that's still the same, but now it's 1, negative 1, 4, negative 2, 9, negative 3. This is y equals the negative square root of x. So what did this do? What did this negative sign do? Reflects the function. I'm going to say it this way. Vertically across the x-axis. I don't know if you see it that way. We've got the function, it's reflecting it vertically across the x-axis. This is the x. Okay? We'll come back to this in a minute. All right, now let's look at the last one here. The negatives on the inside, right? We're going to use the same graph here. We're going to do y equals the square root of negative x. Do you see what I'm doing here? Since the negative's inside with the x, I put negative on the inside with x. Now normally I did 0, 1, 4, 9, but if I put 1 in 4 or 9 in, I'm going to have the square root of negative 4. And that's not going to give me a real answer. And so I'm actually going to put negative 9, negative 4, negative 1, and 0. Because what happens when I put negative 9 into this function? I have the opposite of negative 9, or negative negative 9, which gives me positive 3. Plug negative 4 in, I get 2, 1, and 0. Check this out. I think this is really cool. Notice what happens now. Instead of 0, 0, but instead of 1, 1, it's negative 1, 1. It's negative 4, 2, and it's negative 9, 3. Cool, huh? Oops, wrong spot. Alright, so what happens when there's a negative sign on the inside of the function? I'm going to say it reflects the function horizontally across the y-axis. Okay. Now, I know there's a lot there, but let's talk through this quickly. There's some patterns here that will help you remember this. You don't have to just do straight memorization. Notice what's highlighted in each of these. What do you notice about these three things and their location compared to the function? Do you see they're all on the outside? Plus 2 on the outside, times 4 on the outside, negative sign on the outside. Okay? Over here, notice these locations are all on the inside of the function. Plus or minus d inside times 4, negative sign inside. Now look at the movement. Notice this is moving up and down. Vertical, stretch, reflect, vertical, across the x-axis. Whenever it's on the outside, it's vertical movement, up and down. Whenever it's on the inside, it's horizontal movement. Okay? And then from there, plus or minus, that's what we call shifting. It moves it all up or all down or all left or all right. Doesn't stretch it. When I'm multiplying, it's stretching and shrinking. And when you have a negative sign, it's reflecting. The last thing I'll point out is with these two on the inside, it's, I think, backwards to what we would expect. Plus d moves it left. Times c shrinks it horizontally. And so those are some patterns that you can help you to understand this. Let's keep going here. Now to put it into practice. Describe how the graph of the function can be obtained from one of the basic graphs, then graph the function. Alright, so I'm highlighting the cubed, you see that? What basic function do I have, and what is happening to it? I'm seeing the y equals x cubed function. I'm seeing it move, I want to say move left 6, but since it's on the inside, it's moving right 6 and up 5. So if you need to, go back and look at your cubing function. That's what it looks like. You can see 3 kind of points here, and then the points 2, 8, and negative 2, 8. We can do those exact same things down here. I know it's going to be moved right 6 and up 5. That's right here. So the way I think of it is this is my new x-axis. So I've got a point here, over 1, up 1, over 1, down 1, and then over 2, up 8, which is maybe about here. Down, over 2, down 8, 6, 8. And then I can graph my function. And do you see that this purple graph is similar to this blue graph, only it's over 6, up 5. There we go. Alright, let's take a look at the next one. What's the basic function, or the parent function that you see here? That's a word you'll see as parent, like kind of like a son and daughter, only a parent. So we've got a couple things going on here. We got y equals x squared. We also have times 1/2 and the negative. Notice these are both on the outside. So 1/2 is between 0 and 1. So this is going to be a vertical shrink of 1/2. And this negative is going to reflect vertically across the x-axis. So here we go. Normally, a parabola looks like this. And again, let's look at some of these points on this. See it? 0, 0, over 1, up 1 in both directions, over 2, up 2 squared, or 4 in both directions. Alright, so down here we go still 0, 0. I didn't shift anything anywhere. Now, normally I would go over 1 and up 1, right? But now I'm reflecting vertically, so I'd go over 1 and down 1, but the 1/2 shrinks it half as tall. And it's going to be the same on both sides. Normally I would go over 2, up 2 squared, which is 4, but I need to go down 4, but only half that much because of the times 1/2. And if you wanted to, you could go over 3, and instead of going down 9, we need to go down 4.5. Oops, I'm off a point here. And 4 squared would be 16, half of that would be 8. And so hopefully this is helpful for you to see how we can quickly get a graph from here. When I quiz you on this, test you on this, I'm going to have to ask you questions in ways that ask you to explain and describe from the function. Because I know you can type these things in your calculator and look at them, but I really want you to see the connections between the equations and the graphs. And so that's what I'm going to ask you. Maybe I'll even show you something like this and say, where does the 5 in the function, how does it affect the graph? Or something like that. So please do just practice these skills and practice graphing. That would be good. Alright, let's identify the parent functions here, what's happening, and then I have to stop and have class. Here we go. Parent function. Do you see the parent function 1 over x involved? the plus 3, the minus 2. Hopefully you see this is outside, so this is going to move it down 2. This is on the inside of the function, so it's going to move it, you might think right, but it's backwards. It's going to move it left 3. So left 3 and down 2. This is my new origin, and then this one I'm okay being a little sloppy, just kind of drawing in these two. Okay. Pretty quick, huh? Quicker than typing it in your calculator, I bet. Here we go, parent function here. Hopefully you're seeing the absolute value bars. You're seeing the minus 2, the times 3. Absolute value. Do you remember what that looks like? It's the V shape. Times 3 on the outside of the function. It's going to be a vertical stretch of 3. The minus 2 is going to go down 2. So I go down 2. This is kind of my new origin, so to speak. Normally I would go over 1, up 1, but now I'm going to go over 1 and up 3, because it's 3 times as tall. Do it again, over 1, up 3, and so on. It's absolute value. I'm going to have the same in the other direction as well. Alright, thanks guys. I'm going to stop the video here and we'll pick this up another time.